Many professionals interact with spreadsheets by manually scrolling, filtering, and copying and pasting cells across massive datasets. The software is used as a manual ledger. Scaling data analysis requires engineering the spreadsheet as a programmable logic engine. The goal is to define relationships that allow data to flow and update automatically. This invoice demonstrates that automated end state. Entering a single variable, like 1000, actively generates the description barstool and price 175. That automation is driven by underlying relational mapping and aggregation formulas, operating quietly behind the cell values. Mastering conditional aggregation and relational mapping shifts the professional's role towards systems architecture. You build the logic once, and the software handles the processing. Conditional aggregation is the ability to mathematically evaluate a massive dataset based on strict logical rules. This is the sum-if syntax. It executes filtering and aggregation simultaneously by processing three distinct sequential arguments. The first argument, range, defines the exact boundary or array of cells that Excel is commanded to evaluate. The second argument is the criteria. This is the logical test applied to the range, such as finding a specific text string or applying a mathematical operator to isolate specific rows. The final optional argument is the sum range, which dictates the specific target data to add up once those strict conditions are met. Contrast that programmatic approach with this manual AutoSum setup. The user relies on a dotted marquee line to physically isolate a rigid block of January data. SUMIF eliminates the rigid manual selection of cells. As the underlying data changes or expands, the system dynamically recalculates totals based on the programmed logic. Aggregation summarizes data, but a logic engine must also retrieve it. Relational mapping is the process of linking two disparate tables together. The core mechanism relies on finding a matching identifier, a shared primary key in an external dataset to pull in related metadata. Excel translates this concept into the strict four-part syntax of the VLOOKUP function. The first two parameters define the search space. The value is the shared primary key, and the table array is the absolute boundary of the external database being searched. The index number dictates where the target data lives. The function counts columns from left to right, starting at the primary key, to locate the matching return value. The final parameter requires attention. VLOOKUP defaults to an approximate match. To return precise data, you must explicitly command it to find an exact match by entering false. VLOOKUP successfully creates the first bridge between flat files. However, its rigid architectural structure contains risks when used in dynamic systems. VLOOKUP's reliance on rigid column indexing creates a structural vulnerability. The logic is tethered to the physical layout of the sheet. It suffers from the leftmost column constraint. The function physically cannot search to the left of its primary key, dictating the formatting requirements for your source data. If a user inserts a new blank column into the middle of an established table array, the hard-coded index number breaks. It lands on the blank column, returning 0 or pulling incorrect data. VLOOKUP also lacks native error handling. When a lookup fails, it returns an NA error that cascades through the spreadsheet, affecting dependent formulas. Look at the formula bar in this worksheet. To prevent those cascading errors, you must build a cumbersome workaround, wrapping the VLOOKUP in a nested if-NA function. A system that breaks upon routine structural updates and requires nested workarounds to function cleanly cannot scale reliably. An architecture upgrade is required. XLOOKUP is the engineered solution, serving as the modern standard for relational data mapping. Its primary architectural innovation is decoupling the monolithic cable array into two independent targeted arrays, the lookup array and the return array. This decoupling solves the left-to-right constraint. Because the arrays are independent, the return data can exist anywhere relative to the lookup key. This makes the formula immune to database structural changes. Inserting a column between the specific arrays has no effect on the targeted ranges. XLOOKUP also features native error handling, eliminating the need for nested wrappers. The if-not-found argument cleanly controls the output if a primary key is missing, replacing a volatile error with specific text logic. By decoupling the arrays and integrating error handling, XLOOKUP ensures that relational links remain functional even as the database evolves. Data entry is passive. To operate efficiently at scale, data analysis must be active and programmatic. SUMIF applies programmatic logic to incoming information, automatically filtering and generating conditional insights as the data flows in. XLOOKUP establishes resilient, multi-directional relational links between previously isolated datasets, unaffected by shifting columns. Combining conditional aggregation with resilient relational mapping streamlines the analytical pipeline. It automates the retrieval and calculation steps that are typically prone to manual entry errors. Treating Excel as a logic engine allows you to engineer analytical pipelines that scale as your data grows.